You've probably never looked at a city skyline and thought, this is old technology. But it is. You see, long before humans stacked stone or poured concrete, insects were already building climate-controlled high-rises, underground cities, and lightweight composite homes using nothing but mud, spit, and instinct. Today, on this episode of Insects for Fun, we're talking about insects as architects, because these tiny builders solve problems that human engineers are still trying to master. For insects, architecture is not decoration, it's survival. A structure has to regulate temperature, control humidity, protect against predators, raise young, store food, and sometimes even farm crops. And it all has to be done with minimal energy and biodegradable materials. No blueprints, no supervisors, just millions of tiny decisions guided by evolution. That makes insect architecture one of the purest expressions of natural engineering on Earth, which is really cool to think about. If you want to see insect architecture at its most impressive, we need to look at termites. Some species build towering mounds across African savannas that can reach over 25 feet tall. Relative to body size, that's like humans building skyscrapers miles into the sky. But it's not the height that makes these special. It's actually what's happening on the inside, because these mounds aren't just for protection. They're air conditioners, both for the insects themselves and fungi. You see, termites grow fungus inside special chambers to break down plant material that the termites can't digest on their own. And that fungus needs precise temperature and humidity control, which is solved entirely by the mound using passive ventilation. Air flows through a network of tunnels and chimneys, driven by temperature differences between day and night. Hot air rises and escapes, while cool air is drawn in. This flushes carbon dioxide out and pulls fresh O2 in. No fans, no electricity. Just physics, because the termite mound is shaped and structured in a way that forces air to move, even though nothing inside is actively pushing it. And the thing is, the mound never fully stops breathing. Human architects have directly copied this design to reduce energy use in large buildings, but the termites figured this out millions of years ago. Okay. Now let's talk about paper wasps and the invention of pulp. Paper construction feels relatively modern, considering humans were first writing on stone walls and rocks. But paper wasps have been doing it long before humans learned to write. Paper wasps don't harvest trees or fell branches. Instead, they collect weathered, partially rotting wood. This matters because old wood fibers are already broken down and easier to process. Using their mandibles, the wasps scrape these fibers loose from fences, branches, and buildings, then chew them into a pulp and mix it with saliva rich in binding proteins. The result is a natural composite material, lightweight, flexible when wet, and surprisingly strong once dry. Essentially, it's paper mache, perfected by evolution. The nest is built one cell at a time, and each cell is a hexagonal chamber designed to cradle a developing larva. Still, the geometry also distributes stress evenly across the structure. Hexagons pack tightly and allow the nest to grow outward without collapsing under its own weight. And if you're wondering why don't they cover everything up, well, the open-face design and thin paper walls help regulate temperature and humidity. It prevents mold and overheating. In hot weather, adult wasps fan their wings to increase airflow, turning the nest into a living, breathing structure. The word paper in paper wasp is completely literal. In a sense, wasps invented paper manufacturing without factories, without pollution, and without waste. Every fiber is recycled, every structure is temporary, and when the season ends, the nest simply returns to the environment which it came from. Also, if you've ever had the thought that most social wasp and bee nests look similar on the inside, it's not your imagination. Hexagon cells aren't just sturdy, They're actually incredibly efficient because hexagons hold the most volume using the least material, which is exactly why honeybees use them as well. Any other shape would waste wax, and wax is expensive for a honeybee because it takes about 8 pounds of honey to produce 1 pound of wax. Okay, enough with the fluff. We're now going to talk about ant cities and underground metropolises. Ant nests are indeed cities, and not the poetic kind. They're functioning, regulated, ever-changing communities built entirely underground. Well, for most species anyway. For ants, architecture is inseparable from society because a nest is not just the shelter. It's an extension of the colony's collective body. We're talking many different specialized chambers where temperature and humidity are tightly controlled. Nurseries, food storage areas, and waste disposal zones kept far from living areas. And in some species, massive fungus gardens that serve as the colony's primary food source. Leafcutter ants are a great example because they maintain fungal farms that can weigh hundreds of pounds and require constant airflow, cleaning, and replanting. These gardens are positioned deep underground, where temperatures stay stable year-round, and waste chambers are placed even deeper, deliberately isolated. Did you know that some ant nests stretch more than 6 meters underground? From the surface, you might only see a small mound or a few entrance holes, but beneath your feet could literally be a sprawling metropolis with highways and neighborhoods. Seriously, these nests have traffic systems. Ant highways form naturally as individuals follow chemical pheromone trails, reinforcing the most efficient routes over time. Ants adjust their speed, spacing, and even reroute traffic to prevent jams, much like adaptive traffic systems in human cities. Ventilation is another one of their engineering triumphs. Many ant species build vertical shafts that act like chimneys, allowing warm, stale air to rise and escape while drawing fresh air downward. The depth and shape of tunnels help regulate oxygen levels and humidity without any active control. Once again, physics does the work, just like with our termite friends. And then there's sanitation. Dead ants and waste aren't left lying around. They're transported to designated refuse chambers/dumps, or even removed entirely from the nest. Some ants actually specialize exclusively in waste management, like dump truck drivers and quarantine personnel. The most astonishing part, though, is that no single ant understands the full plan. There is no architect ant. The city emerges from countless small actions guided by simple rules. Dig where it smells right. Drop soil where airflow feels wrong. Follow trails that work. Avoid areas that don't. Out of that simplicity comes staggering complexity. That's why urban planners, computer scientists, and engineers still study ant nests today. Not because ants build cities like we do, but because they solve problems of space, traffic, climate control, and cooperation in ways we're only beginning to understand. Which leads us directly into our next segment of how humans copy bugs. There's actually a special approach in the world of architecture known as biomimicry or biomimetics, which looks directly to nature for inspiration. And insect architecture has influenced far more human inventions than most people realize. One of the most famous examples comes directly from termite mounds. Buildings around the world now use passive ventilation systems modeled after termite airflow, relying on carefully placed vents, thick walls, and natural convection to regulate temperature. These buildings can stay comfortable using a fraction of the energy required by conventional air conditioning. When it comes to bees and wasps, honeycomb geometry shows up everywhere. Engineers use hexagonal structures in airplane wings, spacecraft panels, helmets, and packaging because honeycomb designs are incredibly strong while remaining lightweight. It's the same logic bees use: maximum strength and minimum material. When it comes to ants, ant-inspired designs goes beyond building and into infrastructure. Traffic engineers study how ants form and adjust pheromone highways to reduce congestion. This research has actually influenced adaptive traffic light systems, delivery routing algorithms, and even how data moves through communication networks. Construction materials are also borrowing ideas from insects. Researchers are developing self-healing concrete inspired by insect-built structures that naturally repair cracks over time. Others are experimenting with modular, grow-as-needed housing concepts that mirror how ant nests and wasp colonies expand only when necessary. What all of these ideas have in common is efficiency. Insects build structures that are recyclable, resilient, and perfectly scaled to their needs. Their buildings repair themselves, respond to their environment, and never waste space or energy. That's a lesson we as people are still trying to figure out. And that's going to end this episode of Insects for Fun. Thank you as always for listening, and make sure to rate the show 5 stars on whatever platform you listen. It really helps a lot. And of course, it helps even more if you tell some friends and family or acquaintances that you think might be interested in learning more about insects. Now, of course, there's also a Patreon with bonus episodes, ad-free episodes, vlogs, and some more stuff. So, go check that out if you want to support the show in another way.